Good morning everyone. This is Payavala Bhavagna from Institute of Aeronautical Engineering IARE. I am from the branch Computer Science and Engineering and my roll number is 249518059. Today I am here to explain my topic in complex engineering problems of AIT 2 in the course Essentials of Problem Solving, and my topic is string compression. Now let us quickly get into the topic. Complex engineering problem project, string compression. Now let us get into the abstract part. Abstract. String compression is a fundamental technique in data processing that reduces the size of textual data by exploiting patterns and redundancies within the string. The goal is to encode a string in more compact form without losing the ability to recover the original information. This paper explores various string compression algorithms, their theoretical foundations and practical applications. We review lossless compression methods using run length encoding, RLE, Huffman encoding, Lempel, Ziv, Welch and Burrows-Wheeler transform, analyzing their efficiency in terms and time complexities, space saving and decompression accuracy. Advanced techniques such as grammar based compressions and entropy encoding also discussed with companies to traditional methods in terms of adaptability to different data types. We further examine the role of string compression in domains such as text indexing, bioinformatics, DNA sequence comprehensions and real-time data transmissions, where storage and bandwidth constraints are critical. Experimental results demonstrate that performance of selected algorithms across various databases, highlighting trade-offs between compression ratio and processing time. Finally, we discuss the impact of modern computing paradigms, including parallel and distributed processing, on accelerating compression techniques. The paper concludes with potential directions for future research, including hybrid models and AI-driven compression strategies that learn data pattern from optical encoding. Now let's know about the introduction of string compression. In the era of massive data generation and transmission, the need for efficient storage and bandwidth utilization has become increasingly critical. Textual data in the form of strings constitutes a significant portion of digital information, from documents, logs, and web content to biological sequences and communication protocols. String compression, a subject of data compression, focuses specifically on reducing the size of these textual sequences by encoding them in a more compact representation without any loss of information, thereby enabling more efficient storage, faster transmission, and better overall management. String compression techniques capitalize on the inherent redundancy and pattern in data. For example, repeated characters, common substrings, and predictable sequences can be replaced with shorter representations that occupy less memory. The central challenge in string compression lies in achieving a high compression ratio while maintaining reasonable encoding and decoding speeds. Furthermore, the compression must be lossless, meaning that the original string can be perfectly reconstructed from its compressed form, an essential requirement in domains such as source code storage, medical record, legal documents, and DNA sequencing. Over the years, a variety of algorithms have been developed to tackle the problems of string compression. Classic approaches such as run length encoding, RLE, and simple and effective for high repetitive data. More sophisticated methods like Huffman encoding and arithmetic coding use statistical models to assign shorter codes to more frequent characters. Dictionary-based algorithms such as Lempel-Ziv and Lempel-Ziv-Welch families dynamically build dictionaries of repeated patterns and are widely used in popular compression formats like ZIP and GIF. Additionally, techniques like Burrows-Wheeler transform, also known as BWT, enhance the compressibility of strings by recognizing data to make it more suitable and subsequent encoding. Beyond traditional applications, string compression plays a vital role in modern computing scenarios such as optimizing search engine performance through compressed text indexing, enabling in efficient transmission is concentrated IoT environments, minimalizing memory usage in embedded systems. It also contributes to advances in fields such as bioinformatics, where large scale genome sequence must be compressed and searched efficiently. This paper explores the theoretical foundation algorithm, strategies, and real world applications of string compression. We present a competitive analysis of major compression techniques, evaluate the performance across various metrics, and discuss modern improvements including hybrid and machine learning enhancing methods. Understanding string compression not only provides insight into the broader field of data compression but also equips researchers and engineers with the tools to design more efficient and scalable data holding systems. Requirements and prerequisites. String compression is an essential aspect of efficient data management, particularly in fields where storage space, transmission bandwidth, or processing time are limited. For any string compression technique to be effective and widely applicable, it must fulfill several fundamental requirements. First and foremost, the compression must be lossless, meaning that the original string must be exactly recoverable from its compression version. This is critical in applications where data integrity is paramount, such as in code storage, medical data, or financial records. Additionally, the method used must be achieving a high compression ratio, effectively reducing the size of data without excessive loss of efficiency. However, this must be balanced with speed, or both compression, encoding, and decoding should be performed rapidly, especially in real life systems or large scale applications. Moreover, memory efficiency is crucial, particularly in embedded systems or mobile devices where resources are constrained. The algorithm should be scalable, capable of handling both small strings and massive data sets without performance degrading. Another important requirement of the adaptability of the compression method to different types of data. While some algorithms perform well on high repetitive sequences, others may be more suited for human related text or binary content. Therefore, a flexible design that can adjust to various data structures is desirable. In some cases, error resiliences become a necessity, especially in scenarios involving unreliable networks or physical storage prone to corruption. The compression system should be able to either detect or correct errors during transmission or storage. For broader applicability, the algorithm should be simple to implement and maintain. Ideally, with well documented procedures and minimal computational overhead, should not additionally security and privacy considerations must be acknowledged. Compression should not expose sensitive patterns that could be exploited in encrypted data. Streams or secure environments. Before implementing a compression method, certain prerequisites should also be considered. These include fundamental understanding of data patterns and redundancy, as compression relies heavily in identifying repeated substrings, predictable sequences, or frequent characteristics. The input data should exhibit some degree of regularity, otherwise compression must not be effective or could even increase the data size. Moreover, knowledge of data structures such as trees, dictionaries, or queries is often required, especially in algorithms like Huffman coding or Lempel-Ziv variants. Familiarity with the entropy and statistical modeling can also be beneficial. So many advanced techniques depend on understanding the distribution of symbols within the string. Lastly, the computing environment includes available memory. Memory processing power and storage medium must be assessed to ensure that the chosen compression technique aligns with system capabilities and constraints. Methodology. The methodology of string compression involves a systematic process aimed at reducing the size of string while pursuing all essential information to allow the accurate reconstruction. This process generally consists of several stages, starting with data analysis, followed by the selection of suitable algorithm, compression process itself, and finally decomposition and validation. Each stage is crucial, ensuring that the compression technique is both efficient and lossless. This first step is a methodology is to perform a preliminary analysis of the input string. This includes identifying patterns such as repeated characters, frequent substrings, and character distribution. The nature of the input data, whether it is highly repetitive, natural language, binary code, or biological sequence, directly influences that choice of compression algorithm. For example, strings with long sequence of repeating characters are suitable for run length encoding RLE, where those variable repetition pattern may be benefit from dictionary based algorithms like Lempel-Zip-Welch LZW. Once the data characteristics are understood, the next phase involves the selection and application of appropriate compression algorithm. Common methods include statistical coding, techniques like Huffman coding, while assigns shorter codes to more frequent characters, and arithmetic coding, which uses interval to represent the entire string as fraction. On the other hand, dictionary-based algorithms such as LZ77, LZ78, and dictionary during compression LZW replace repeated substrings with references to earlier occurrences, building a dynamic dictionary during compression. Another powerful technique, the Burrows-Wheeler transformer, recognizes the input data to improve the complexibility, especially when used in conjunction with a move to front encoding entropy coding. The compression process begins with tokenizing or transforming the original string based on the chosen method. For Huffman encoding, a frequency table is constructed, followed by the generation of a binary tree to derive optimal codes for LZW. The string is passed into substrings which are added to dictionary and placed with the corresponding indexes. The output of this phase is compressed string or file, often represented in binary form. From compression, the decompression process is equally important and must precisely reverse the steps taken during compression to reconstruct the original string without any loss. Each algorithm has a dedicated decoding process. Huffman decoding uses the same binary tree to retrieve characters from binary codes, while LZW decompresses rebuild the dictionary during recoding during the received indexes. Successful decompression is typically validated by comparing the reconstructed string with the original input to confirm integrity. To support performance evaluation, the methodology often includes matrices for accessing complexion quality, such as compression ratio, time complexibility, and memory usage. Experimental validation may involve running the compression algorithm or multiple datasets to measure the effectiveness across varying input types. In some cases, optional post-processing steps such as encryption or error checking may be integrated into the pipeline depending on the specific use case. In modern applications, hybrid technique and machine learning assisted models are also incorporated to improve adaptability and performance, further expanding the methodology into intelligent compression systems. Overall, the methodology of string compression is a blend of theoretical understanding and practical implementation, requiring careful algorithm selection, data preparation, and iterative testing to ensure both efficiency and fidelity. Now let us look at the code. Code for run length encoding goes like this. We'll take a variable as we'll take the keyword as defined, and we'll take a compressed string, input string, and the code basically shows that when you give an input of a repetition of 2 or more than 2 alphabets or symbols, it after the compression, characters are replaced by, when you look at the explanation, the input is triple A and 5 B's, 2 C's and 5 D's again. The compression is consecutive characters are replaced by the characters followed by its count. There are 3 A's, so it is A3. There are 5 B's, so it is 5 B5, etc. So the output would be something like A3, B2, B5, C2 and D5. The function also ensures that if the compressed string is not shorter than the original, it returns to the original to avoid unnecessary expansion. If the compressed string is not shorter than the original one, it automatically had to return to the original thing, original image, because unnecessary expansion is not encouraged. If at all, if you want to decompress the string back into its original form, you again use this, and you give the keyword as decompressed string and compressed string, and you give all the details, and then it will compress it back to the number of count ones. Now let us look at some applications. String compression has a wide range of practical applications across various domains in computer science, data management and communicative technologies. One of the most common uses is the file storage and archiving. By compressing textual data such as documents, logs and code files, organization can significantly reduce the amount of disk space required, leading to more efficient use of storage infrastructure. Formats like ZIP, gZIP and RAR rely heavily on string compression algorithms such as Lempelzevich and Huffman coding to minimize file size without compromising data integrity. In network communication, string compression plays a crucial role in reducing bandwidth usage and improving data transmission speed when data is transmitted over the internet. For example, in emails, HTTP responses or instant messages, compressing strings can make transmission faster and more economical, especially in bandwidth transmission. Environmental web servers after use compression techniques like gZIP to reduce size of HTML, CSS and JavaScript file before sending them to browsers, thus accelerating website loading time. Another major application lies in database management and indexing systems, where string compression is used to store large volumes of textual data more efficiently. Compressed storage reduces memory overhead and spreads up query execution by minimizing the amount of data that must be read from disk. Search engines also use compressed inverted indexes to improve the speed and efficiency of keyword search across a vast text corpora. In the field of bioinformatics, string compression is vital for handling the massive volume of genetics data generated by DNA sequencing technologies. DNA sequences are essentially long strings of characters A-C-G-T. Compressing them allows the researchers to store and analyze genomic data more efficiently. Special algorithms has been developed for biological sequences that exploit their unique patterns and repetition. String compression also finds use in embedded systems and Internet of Things IoT devices where storage and memory resources are extremely limited. In such systems, configurations like sensor logs and communication protocols often use compressed strings to conserve resources and prolong battery life. Similarly, mobile applications leverage compression to reduce download size and improve responsiveness, especially in scenarios involving limited connectivity. In software development and source code management, string compression helps in reducing the size of source files, configuration scripts, and code libraries. It is especially used during software packages and development, where compression bundles ensure faster installation and updates. Additionally, digital communication formats such as PDFs and docs and image metadata storage string compressions to keep file size manageable without altering visual or structural content. Finally, in machine learning and natural learning process, compressed string representation helps in processing large text database, reducing model input size, and improving computational efficiency. Compression can also use for model distillation, where large language models are compressed into smaller, more efficient, formats for developing on edge device. Now finally, let's come to a conclusion. String compression is an essential technique in modern computing, playing a vital role in optimizing data storage, reducing transmission costs, and enhancing overall system performance. As the volume of digital information continues to grow exponentially, efficient data representation has become crucial than ever. String compression addresses the challenge by reducing redundancy within data, allowing it to be sorted and transmitted in more compact form without sacrificing integrity. This is particularly significant in fields where data accuracy is critical, such as in medical records, legal documents, specific research and software development, where even a minor loss or alteration of information can have serious consequences. Over the years, numerous string compression algorithms have been developed. Each has its own strengths and suitable applications. Simpler techniques such as run length encoding and effective for data with frequent character repetition, while more advanced methods like Huffman encoding, arithmetic encoding, and director-based algorithms like LZW offer better compression ratios for complex data. The choice of compression algorithm depends on various factors, including the type of input data, the need for speed and efficiency, system resources constraints, and the intended use case. In many real-world scenarios, hybrid approaches and algorithm adaptations are employed to achieve the best balance compression effectiveness and computational cost. String compression is not only a theoretical concept but also a highly practical tool with wide-ranging applications. It is used in file achieving web development, mobile application communication, protocols, bioinformatics, and even machine learning. Compression enables faster downloads, more responsive user experience, and lower strange costs in constrained environment as IoT devices and embedded systems. Compression is also often a necessity due to limited memory and processing capabilities. It is also indispensable in transmitting large volumes of data across networks where bandwidth is limited or expensive. Furthermore, a new challenge arises, such as the need for secure data transmission, error resilience, and real-time processing. The field of string compression continues to evolve. Research and are actively exploring more adaptive, intelligent, and domain-specific compression methods that can learn from the structure of data and optimize compression dynamically with the integration of machine learning. The future of string compression is likely to feature more context-aware and self-optimizing systems that further push the boundaries of efficiency. In conclusion, string compression is foundational technology and significantly contributes to the efficiency and scalability of the modern computing systems. It reduces the overhead associated with data management, improves performance across platforms, and supports the growth of data-centric applications. As data continues to expand in both volumes and complexities, string compression will remain a critical area of research and applications, driving innovations in fields that rely on compact, reliable, and rapid data process. These are few of the references from which string compression is extracted from. Data compression, the complete reference written by him. His name is David Salomon. Introduction to Data Compression, written by Khaled Sayyoun. And A Universal Algorithm for Sequential Data Compression, written by Ziv J. Lempel A. Compression of individual sequences via variable rate coding, written by ZJ and Ziv J and Lempel A again. The source that we took is Wikipedia of data compression, and Huffman coding is taken from Geeks for Geeks. same with the lymph wells of one as well. Thank you.